This video will cover the information that you need to know on the chemistry portion of Bio 201. If we take a look at the objectives, you probably know most of the objectives already, having taken some other classes before you got into this one. You should know what matter and the states of matter are. You should know what an element is. You should know what an atom and a molecule are. You should have some familiarity with ionic bonds and covalent bonds, and the rest of it, I wouldn't be surprised if you didn't know it, and it's okay with that. I'm okay with that because I'm going to help you with that. So if we take a look at matter, of course, matter is made out of atoms, and it comes in three states: solid, liquid, gas. The two states that we see in our body, well, then there's plasma. So we can see all three states of matter in our body. We have solid in our bones and our muscles, we have liquid in our blood, and we have gas in the air that's in our the alveoli of our lungs. All right, as far as those atoms that comprise our body, the majority of them are these four: carbon, hydrogen, oxygen, and nitrogen. We abbreviate them CHON. And remember that elements are the smallest unit of matter, made up of the same type of atom. So all the atoms that we consider carbon will all have six protons, 6 electrons. Hydrogen will all have 1 proton, 1 electron. Oxygen, so on into their various characteristics. In addition to these 4 elements, in fact, these will make up 96% of the elements of our body. And then we have trace elements. We have other things from the periodic table, different kinds of atoms that we need to carry out proper function within our body, but we don't need them in very large amounts. And so I put an example: magnesium, potassium, sodium, calcium, sulfur, and phosphorus are the major ones of the trace elements, and there are about 25 trace elements. But remember, the 4 elements of living things that make up 96% of our matter: carbon, hydrogen, oxygen, and nitrogen. All right, so as you know, an atom, smallest unit of an element. We've got a nucleus with protons and neutrons that have, protons have a positive charge, neutrons have no charge, and electron cloud around the outside has a negative charge, or the electrons have negative charges. Here you can see their position within an atom. So we have the nucleus here in the middle with the protons and the neutrons, and then around the outside we have the electrons. In this planetary model, it just shows where they're sitting. So this happens to be a helium atom, where you would find the electrons, but in the orbital model, this shows the actual places that they occupy. And so any of this region in here, and this is the quantum model of an atom, and so we can't pinpoint exactly where the atom is, but I mean the electron is, but we know it can exist anywhere in this area. All right, now one of the things that we do, or we have within our bodies, are solutions. So these are not compounds, these are not elements that have been bound, or atoms that have been chemically bonded together. They're just in a bunch together. They're in a mixture, for lack of a better term. And so mixtures are usually solutions that we have within our body. So there are 2 kinds of mixtures. We have homogeneous mixtures and we have heterogeneous mixtures. So the homogeneous mixtures will have a solute, which is usually the solid part. It could be 2 liquids mixed together to make a homogeneous mixture. If you were to put, let's see, like, mixed alcoholic drinks. So I don't even know, I don't even drink, so I don't know why I'm using this example, like rum and coke, or club soda and some other alcoholic beverage. Why can't I think of a non-alcoholic one where you mix 2 liquids together? Pepsi and milk. I don't know. I can't even think of one. Sorry, you guys. But anyway, but the solute is usually solid, and then the solvent is the liquid portion. So Kool-Aid is a perfect example. I guess I'm stuck on the Kool-Aid thing in my head. The solute would then be the Kool-Aid powder stuff, it comes in the pouch, and then the sugar. So those would be solutes, and then the solvent, of course, would be the water, the liquid portion. And when they mix together, they're homogeneous because we can't see the individual parts. And so I'll show you an example of that in just a minute. But most of our nutrients, wastes, hydrogen ions, all that in solution are in the plasma of our blood or the interstitial fluid between our cells outside of our capillaries. And so those would be homogeneous mixtures. So interstitial fluid, blood plasma, there are going to be a lot of components dissolved within that, and that makes them solutions. A heterogeneous mixture, on the other hand, is where you can actually see the solid particles typically that are associated in that mixture. Colloids would be like the cytoplasm of a cell, and suspensions would be blood as a whole, not the plasma of blood, but all the blood together. So let me show you a picture of that. So here in a solution, the solute particles are tiny. They don't settle out or scatter light. So mineral water is a great example because there's a lot of minerals, obviously. So we have sodium and potassium and calcium and other kinds, probably some magnesium, dissolved within the water, but we can't see them. We can taste them. We know that they're there. And if we let the water evaporate and leave the solute behind, then we'll see that. But otherwise, we're not aware of them being there. So that makes that a solution. Okay, a colloid, on the other hand, the solute particles are larger than in a solution, scatter light, do not settle out. This isn't, Jello by itself is not the greatest example, but if I made fruit salad, so if I made Jello salad, I put fruit cocktail in there, that would be a great example of colloid. So you would have the fruit cocktail embedded within the Jello-ness, the gelatin that solidifies within there. You can see the solid particles. Okay, so you can't in Jello. I don't know why they use that, but our cytoplasm is a great example of a colloid because we have the cytosol, we have the background material that the organelles are suspended within or held within, and so or anchored to, I guess you could say that too. So that makes our cytoplasm a colloid. Then a suspension, the particles are very, very large and they will settle out because of gravity. They're too heavy. If you don't keep them mixed up, they'll fall to the bottom. And so that's why blood is such a great example of a suspension, because here is unsettled blood. When our blood is coursing through the blood vessels, it's constantly being mixed together so the solute particles can't settle out of solution. However, if you let that blood stop moving, then the heavy stuff, so the red blood cells, white blood cells, and platelets will sink to the bottom, and then the plasma, the liquid portion of blood, will be up here on the top. So this is a suspension. Blood, whole blood, is a really great example. This is why it's so important for us to keep moving in our appendages, because if we sit for any great length of time and the blood isn't circulating very well, like in a varicose vein or something like that, the blood will separate. And once the cells down here at the bottom, particularly the platelets, once they're not moving anymore, they like to stick to each other. And when they stick to each other, then we've got a clot on our hands. We got the beginnings of a clot. So then you could get what's known as a DVT, or a deep vein thrombosis. My mom used to have one because she's relatively immobile. I mean, she gets around, she has a walker, but she's 95, so she doesn't, and she has a really bad knee. So she doesn't get around very well, and there was a time a couple of years ago where she did develop a DVT in her femoral vein, and so we had to get her some blood thinners, some Coumadin, to help decrease that clot and the likelihood of those platelets sticking together. So got to keep our blood moving, and we'll talk more about that next semester in 202 when we get into blood. All right, now if we do want to create new matter with the atoms, we need to chemically combine them together in a process called bonding. So there are two ways that we can bond. We can bond ionically, or we can bond covalently. In ionic bonding, the atoms involved are going to donate electrons to create ions that are then attracted to one another to form molecules like sodium chloride. So let me show you how that works. It's a lot easier to show you a picture. Okay, typically sodium has atomic number of 11, so it has 11 protons, has 12 neutrons. We don't really care about that. But it's going to have an equal number of electrons. So 11 protons, 11 electrons. Chlorine is going to have 17 protons and 17 electrons. Now, if we take a look at where the electrons are stationed outside of the cell, we can see that in both of these atoms, we have 2 electrons in this first level right here, and then we have 8 electrons in the next level right here in both of them. And then out here in sodium, we have 1. So what the atoms are trying to do is get this filled. So this, the very outer level, we call these valence electrons. So an atom, when it wants to bond with something ionically, is either trying to get rid of this extra electron, or the atom is trying to pick up an extra one so that it can be filled with 8, because it'll be filled with 8 like the other level. So sodium will donate this electron, it will leave, and then by leaving, it will give you 10 plus charges, but 11 plus charges, but only 10 negative charges. So now it doesn't balance out. So this sodium atom now becomes an ion because it has a charge. So this will become positively charged because it lost a negative charge, and so it has an extra positive charge, therefore making it so positive. And I'll show you in the next slide. And then chlorine, once it picks up an extra electron, it'll now have 18 electrons, but only 17 protons, so it has an extra negative charge. So here you can see there's the positive charge in the sodium atom, and here's the chlorine or ion, and the extra electron here giving chloride an extra negative charge. And when we pick up an electron and become a negatively charged ion, then you put "ide" on the end. So fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, and so on. So now this positive charge is attracted to this negative charge, and then we get a brand new compound called sodium chloride. And we know that chemical bonding has occurred because the product of the bonding looks nothing like the 2 parent atoms. So sodium is a silver, very soft, highly reactive in oxygen and water atom or substance, matter. And chlorine, when it's by itself, is a green toxic gas at room temperature. But when you put sodium ions with chloride ions, then sodium chloride, as you are very familiar with, has that crystalline white structure to it, very dissolvable in water and non-toxic. So because these ions are attracted to one another, they're going to form a very regular pattern, a very crystalline pattern. And so that's why salt looks all crystally, is because of how the ions are lining up when they bond with one another. Okay, so that is an ionic bond. So things that are in the very first column of the periodic table, the metals, and then, or the earth metals, and then the second column, the alkali earth metals. Then if you go over to the second to last column on the right, the halogens, when those ions that we need in our body, or those electrolytes that we need in our body, will be delivered in the form of a salt, because of ionic bonding. Everything else that we have in our body is due to covalent bonding. So this is a situation where the elements cannot donate electrons, or the atoms cannot donate electrons, so instead they share electrons to form molecules. So here's carbon, and it's going to bond with hydrogen. So this carbon atom, if you notice, has 4 valence electrons, 4 electrons on the outside. And remember, we said we want 8 to be happy on the outside. So this carbon atom wants 4 more electrons. Well, hydrogen is going to be, because it's the simplest and it only has one electron, notice that the very innermost level has 2 electrons. Well, he would like another electron. If he donated his electron to carbon, then he would have none. So he wouldn't be happy. So he has to be happy with 2, and I don't know why carbon for me is always a girl, but she wants 4 more. So this hydrogen is going to share this electron with this electron, so we're going to share a pair of electrons in this location. This hydrogen is going to share an electron right here, so this pair of electrons is going to form right here, and then this hydrogen is going to form, or is going to share electrons right here, and then this hydrogen will come over and form electrons right there. So now you can see we have pairs of electrons being shared, and so then we call that covalent bonding. And when we abbreviate that, this line represents pairs of electrons, single bonds. And we'll talk more about that in the next lecture. What happens when I get two lines, like an equal sign, or three lines in there? But we'll do that in the next lecture. All right, now, when you share things, you know, there's the way where we're supposed to share, where we share things evenly, and then when we're 4, we don't want to share things, and so we have unequal sharing. That same thing happens with electrons. It depends in covalent bonding. It depends on the nature of the nucleus, whether it has more power to hang on to that extra electron than the atom that's sharing that electron with it. So we get what's known as a polar covalent bond, where we have the unequal sharing of electrons, which is going to create positively and negatively charged ends to a molecule, and I'll show you a slide of that in a minute. The most common polar compound that we have in our body is water. Super, super common, and the reason why we need water in our bodies, the 6 different functions of water in our bodies, is due to its polar covalent bonding and the characteristics that arise from water by sharing its electrons unequally with hydrogen. But again, we'll do that in the next lecture. Phosphates in our cell membrane and our phospholipid bilayer. The phosphate portion is also a polar compound, and again, we will discuss later the significance of that. All right, so here are different ways that we can covalently bond. So we have a single bond right here. Notice oxygen can bond with itself and share 2 pairs of electrons. So when we draw that, we call that a double bond, that equal sign. Or hydrogen will actually share 3 pairs of electrons because they need 3 more electrons in their outer level, and so it will actually share 3 electrons with itself. And so we can sometimes get triple bonds. Again, we'll talk more about that in another lecture. All right, so here shows that even and uneven sharing of electrons. If we look up there at the top in carbon dioxide, notice that the molecules are linear and symmetrical. They look exactly the same. You cut them top to bottom, side to side, whatever, you're going to get the same molecules shape. You're going to get the same amount of carbon and the same amount of oxygen. On the other hand, if you have water, it's not symmetrical. You can't slice it anyway and always get the same, because if I sliced it this way, I might get only portions of hydrogen, but if I slice it this way, I only get 1 hydrogen, you know. So it's not exactly symmetrical, and so what happens is that the oxygen right here has a bigger nucleus than what the hydrogen ion or the hydrogen atoms do, and so it's going to tug on the 2 electrons that are being shared with hydrogen more than the nucleus down here. And so the electrons will spend more time out here on the oxygen end of the molecule, thereby giving it a slightly negative charge. So this delta negative just means that there's a slightly negative end. Then on the hydrogen side, because the electrons are hanging out over here, there's just positive protons on this side. So it gives the water molecule, the whole molecule itself, a slightly positive charge. So this negative side can be attracted to 2 positive charges, and then each of these positive sides can be attracted to 1 negative charge. And I'll show you what you can do with that in another lecture. All right, so here is nonpolar, evenly shared electrons, carbon dioxide, hydrocarbons in the membrane. So the lipid portion of a phospholipid bilayer, those are all nonpolar. Every lipid molecule in our body is a nonpolar substance. Those are really the only, you know, if it's covalently bonded, those are the only things, carbon dioxide and the lipids. Everything else is a polar molecule. All right, so this just shows strength of molecules, how they form, whatever, but you don't need to learn this. Well, actually, no, you don't need to know too much about that. Just know complete transfer, unequal sharing, equal sharing. Okay, now here is what we can do if a molecule is polar, so it has a positive side and a negative side. We can form what are known as hydrogen bonds. So in a hydrogen bond, hydrogen atoms are attracted to the negative end of another polar covalent molecule. So now we're getting molecules attracted to each other. Before we just had atoms attracted to each other, but now we're making molecules attracted to one another. And so you can put molecules together in bunches, for lack of a better term, other structures. So for example, the rungs of a DNA molecule. If you've seen, DNA looks like a twisted ladder. Those nitrogenous bases that are hooked together in the center of the DNA molecule are hooked together by hydrogen bonds. So water, because we said it's super, super covalent, polar covalent, it's going to attract to itself. So if we look at right here, here is the negative side of one water molecule that's forming a bond with this positive side of the hydrogen. Okay, so there is one hydrogen bond right there. Now this hydrogen right here is attracted to this negative side of a different water molecule. Okay, so now here are the two molecules that are occupying the hydrogen spots. But look at what can happen on the oxygen side. It can bond to two different water molecules at the same time because it's got two electrons that are hanging out a lot over here on the oxygen side. So that electron is going to be attracted to the positive proton in this hydrogen ion, forming this hydrogen bond. And then the other electron is going to be attracted to the positive proton here on this hydrogen side of this water molecule. So by bonding together with itself, water creates a bunch of properties. Again, we'll talk about it in another lecture. But one of the properties that it creates is surface tension. And surface tension can be super good in some cases and it can be super bad in other cases. And we'll discuss that particularly when we get to respiratory system. But we'll talk about why we want water to have these hydrogen bonds for other things that are more common. So look at what our water strider can do. So the water strider can walk on a pond because the high surface tension of water result of combined strength of its hydrogen bonds. So each molecule at the surface of the water is bound to 3 other water molecules. Okay, so here's this, or 4 other water molecules. So here's one water molecule and it's bound to 1, 2, 3, 4. So every water molecule is bound together and it creates this sheet, this continuous surface there because the water wants to hang together. So by having these super long feet, can you see how long his feet are? Super, super long, like snowshoes. So what he does is put a little bit of force in each part of his foot, distributing the force across the surface area of his foot and therefore not breaking through the surface tension. But what if he just had his little peg leg right there? You know what's going to happen. He's just going to poke right through the water and sink. But because he can take advantage of surface tension by having this large surface area of his feet, he doesn't sink. And I love this. This is a little microcosm on a pond ecosystem, because usually when you think of ponds, you think of the seaweed, well, the grass, and moss and stuff that grows under the water, and the little fish that eat that, and the bigger fish that eat that, and all the animals involved in a food web in a pond. We don't consider this little microcosm right on the surface of the pond. So this little water strider guy is a predator, and he's looking to eat anybody that happens to land on the surface of the water, or the little cow-like insects, that eat the plant material that would be, maybe just on the surface or right below the surface. So he's going to be like a mountain lion on this pond ecosystem, right on this surface, just at the surface. He does not go down into the water. I know you don't care, but it's really fascinating to me, and I love, we got predators and prey that just live right on this surface tension of water, right at the surface of a pond. You'll find I like to tell you other things. Just go with it. Amuse me. Maybe you'll need to know that some other time in your life. All right, so let's go into chemical reactions. So in addition to bonding, we need, actually some chemical reactions allow different kinds of bonds to take place. And so when we looked at the characteristics of life, one of the characteristics of life was metabolism, where we build things up and we break things down. So remember that anabolic means to build up and catabolic means to break down. So when we're doing those reactions that are anabolic, that build things up, what we're going to do is take two different objects, and then we're going to combine them together into one object. And so we call this a synthesis reaction. And so all synthesis, you know, you make something, you synthesize something. And anabolic means to build up. So we're going to make something from two smaller substances. We're going to find this in rapidly growing tissues. Obviously, we're going to take basic building blocks and we're going to put them together and make things. So let's say that you were working out and your muscles were super sore because you did a lot of heavy lifting, and now your proteins, in your muscles need to be rebuilt. So that would be a really good example of an anabolic process where amino acids that make up proteins are being assembled into larger proteins. So here is that example. So our proteins that make up our muscles that do the contracting so that we can produce force are these chains. Now they've got a lot of other structure we'll talk about in the next lecture. But this is the primary structure of a protein, where all we do is put these little orange lozenge thingies together with a little bond in between. And so a synthesis reaction is going to take the individual amino acids and hook them together in a long chain. So this is synthesis reaction. We actually call it dehydration synthesis. We'll talk about why at another time. All right, now what if we want to break them down? So let's say that the food that we eat comes in cow protein. Well, I don't want cow protein to build my muscles with. I need human protein. So what I'm going to do is break down that cow protein into its individual building blocks in the digestion process. I'm going to absorb those amino acids, and then I'm going to build my own proteins with that. So decomposition is a digestive process, is an example of a digestive process. So here is my big molecule, and I want to split it into its component parts. So catabolic means to break down. If we take glycogen to glucose, or if we take protein to amino acids. So I'm going to use this glycogen to glucose example because I really need you to understand early on in your anatomy and physiology life what glycogen is. So when we eat glucose, not all of our glucose is going to go to our cells for immediate energy. So our cellular respiration, we're going to we need that, you know, and in order to make ATP, we need glucose molecules. Well, we need to store some of them. We're not going to use all of them up. And so our liver is going to take some of these glucose molecules and combine it into this structure right here called glycogen. So each individual green hexagon is a glucose molecule. And so in our liver and in our muscle, we will be storing this glycogen for when I need it immediately. So when it's time to increase my blood sugar levels by taking glycogen out of my liver, I need to break these bonds in here. So when I break up these bonds, that's going to be a decomposition reaction, and then the individual glucose molecules will go out into the bloodstream so that the rest of my cells, my brain, my muscle, and whatever, will be able to use the glucose for what it needs for cellular respiration. All right, now, sometimes in exchange reactions, we're going to trade things. So we're going to take this molecule and add this atom, and then we're going to switch it up. So we're going to pop off the B and put the C and the A together. Or we could take A and B and C and D and rearrange everything into A and C and B and D. And that's what, excuse me, that's what we do with cellular respiration photosynthesis. So I'll show you how that works in just a minute. But here is a good example of just a basic exchange reaction when we have ATP. So here is our ATP molecule with 3 phosphates on it, and here I have a glucose molecule. And so what I want to do is take something from my ATP molecule and hook it onto my glucose molecule. So I'm going to take a phosphate group off. I'm going to break this red bond, squiggly bond right here, and a bunch of energy is going to be donated to this glucose molecule so it can do whatever it needs with it, and it's going to have a phosphate attached to it. Then what I'm left with here is adenosine diphosphate. So I have two phosphate groups on here, so it's not tri anymore, it's diphosphate. Okay, so that's an exchange reaction where the bonds are made and broken in 2 cases. So I broke this bond and then I made a bond right after that. All right, I'll show you the cellular respiration example in another video. So that ends the first part of the discussion, because that will now take us to the next set of objectives.